Did you know that nearly 95% of the universe is completely invisible to us? That's right, everything we can see with our most powerful telescopes, all the stars, galaxies, and swirling cosmic dust, make up just a tiny fraction of what's actually out there. The rest, it's hidden in the shadows, made of mysterious substances like dark matter and dark energy, forces so enigmatic that even our brightest scientists are still scrambling to understand them. And that's just the beginning. The cosmos is full of secrets, weird wonders, and mind-bending phenomena that defy everything we think we know about reality. That's exactly what we're diving into today. This video is your ticket to uncovering 30 of the most astonishing, little-known truths about our universe, facts that will make you see space in a whole new light. We're talking about black holes that warp time itself, galaxies colliding in slow-motion dances, and particles that vanish into thin air. These aren't just random tidbits, they're pieces of a grand cosmic puzzle, clues that help us unravel the deepest mysteries of existence. And trust me, by the time we're done, you'll never look up at the night sky the same way again. Think about it, every time you gaze at the stars, you're peering into a vast living story, one that's still being written. The universe isn't some static, unchanging backdrop. It's alive with energy, violence, and beauty beyond imagination. And the best part, you don't need a degree in astrophysics to appreciate it. Whether you're a casual stargazer or a full-blown space enthusiast, these hidden truths will spark your curiosity, challenge your assumptions, and maybe even leave you with more questions than answers. Because that's the magic of space. The more we learn, the more we realize how much we still don't know. So buckle up. We're about to take a journey into the unknown, and trust me, you won't want to miss a single second. Let's start with one of the biggest cosmic mysteries of all, the fact that most of the universe is literally missing. Picture this, if you scooped up a handful of the cosmos, only 5% of it would be the stuff we recognize: stars, planets, gas, and dust. The rest invisible, undetectable, a ghostly presence scientists call dark matter and dark energy. Here's how we know it's there. Galaxies spin so fast that, by all rights, they should fling themselves apart. But they don't. Something invisible, dark matter, acts like cosmic glue, holding them together with its gravitational pull. And then there's dark energy, an even stranger force pushing the universe apart faster and faster. Think of it like this: if the universe were a loaf of bread baking in an oven, dark energy would be making that bread expand at an accelerating rate, as if the oven itself was stretching. The wildest part, we have no idea what either of these things actually are. Dark matter doesn't emit, absorb, or reflect light. It's completely transparent. We only sense it because it tugs on visible matter, like a shadowy hand bending the path of light from distant stars. And dark energy, it's even more baffling, a kind of anti-gravity woven into the fabric of space itself. Scientists have been chasing these phantoms for decades. They've built underground labs, launched space telescopes, and even smashed particles together at near light speeds, hoping for a clue. But so far, the universe isn't giving up its secrets easily. Some theories suggest dark matter could be made of undiscovered particles, while others wonder if we've got gravity all wrong. And dark energy, it might be proof that Einstein's equations need rewriting, or that our universe is just one bubble in an infinite cosmic foam. What's certain is this: the universe is far weirder than we ever imagined. The stuff we see, the glittering stars, the swirling nebulae, is just the tip of the iceberg. Beneath it all lies a vast, hidden ocean of mystery, and every answer we find only leads to more questions. If you thought dark matter was strange, wait until you hear about the cosmic equivalent of a giant magnet hidden behind our own galaxy, the Great Attractor. This colossal mystery in space exerts such an immense gravitational pull that entire galaxies, including our own Milky Way, are being dragged toward it at a staggering 14 million miles per hour. That's fast enough to cross the entire United States in less than a second. But here's the catch, we can't even see what's pulling us. The Great Attractor lurks in a region of space astronomers called the Zone of Avoidance, an area obscured by the dense clouds of gas and dust in our own galaxy's plane. Imagine trying to spot a lighthouse through thick fog while standing in the middle of a sandstorm. That's the challenge scientists face when studying this gravitational behemoth. Even our most advanced telescopes struggle to peer through the Milky Way's cosmic clutter, leaving the Great Attractor frustratingly out of view. What little we do know comes from observing the strange behavior of galaxies around us. Like leaves caught in a river's current, thousands of galaxies are all streaming toward the same invisible point. Early measurements suggested the Great Attractor might be a massive cluster of galaxies, but its pull is far stronger than any ordinary cluster could explain. Some theories propose it's not just one structure but an immense supercluster, a knot in the cosmic web where filaments of dark matter and galaxies converge. Others speculate there could be something even more exotic at work, perhaps a concentration of dark energy or a flaw in the fabric of space-time itself. The mystery deepens when you consider what lies beyond the Great Attractor. Observations reveal our galactic neighborhood isn't just moving toward this one point, it's part of an even larger flow, as if the Great Attractor itself is being pulled by something greater. This has led scientists to identify an even more enormous structure called the Shapley supercluster, located over 600 million light-years away, which may be the true master puppeteer in this cosmic tug-of-war. What does this mean for us? Well, on human timescales, there's no need to worry about being sucked into this gravitational whirlpool. The distances are so vast that even at 14 million miles per hour, it would take billions of years to reach it. But the existence of the Great Attractor forces us to rethink our place in the universe. We're not just floating aimlessly through space, we're caught in an intricate dance of gravity, one that reveals just how much of the cosmos remains hidden from view. Every time we peel back one layer of mystery, we find another waiting beneath, proving the universe still has countless secrets left to uncover. But as massive and mysterious as the Great Attractor is, it's not the only cosmic oddity that defies explanation. Imagine a region of space so empty, so vast that it feels like the universe forgot to fill it in. That's the Boötes void, a staggering 330 million light-year wide bubble of almost nothingness. To put that in perspective, if you placed our Milky Way inside it, you'd have to travel a quarter of the way across the void just to reach the next galaxy. It's one of the largest known structures in existence, and yet it's eerily vacant, earning it the nickname the Great Nothing. How does something like this even form? Normally, the universe looks like a web with galaxies clustered along invisible threads of dark matter, intersecting at dense nodes. But the Boötes void is the opposite, a gaping hole in that web, a cosmic desert where galaxies are few and far between. Scientists first spotted it in the 1980s, and ever since, they've been scrambling to explain how such a void could exist. Some think it's the result of smaller voids merging over billions of years, like soap bubbles combining into one gigantic empty space. Others propose it might be evidence of an ancient, unimaginably powerful event, something so catastrophic it cleared out everything in its path. And then there's the wilder theory, what if it's not natural at all? Some have speculated that an advanced civilization, far beyond our understanding, could have harnessed the energy of entire galaxies, leaving behind this void as a byproduct of their technology. It's a fringe idea, sure, but it speaks to just how baffling this structure is. The truth is, we don't know, and that's what makes it so fascinating. What we do know is that the Boötes void challenges our understanding of how the universe organizes itself. Voids aren't uncommon, but one this size shouldn't exist according to our best models. It's like finding a mile-wide crater in the middle of a city with no explanation. How did it get there? What force could carve out such space? Every galaxy we do find inside the void becomes a precious clue, helping astronomers piece together this cosmic puzzle. The more we study these enormous, empty regions, the more we realize how much we still don't understand about the large-scale structure of the universe. The Boötes void isn't just a curiosity, it's a reminder that space is full of surprises, and some of them are hiding in plain sight, waiting for us to look closer. At the smallest scales imaginable, the universe doesn't behave like a smooth, predictable fabric. It's more like a bubbling, frothing sea of chaos. This mind-bending concept is called quantum foam, and it suggests that space-time itself is seething with tiny, fleeting disturbances. Imagine zooming in on the surface of a pond until you see not just ripples, but a churning mess of bubbles constantly forming and popping. That's the essence of quantum foam, where the very framework of reality becomes unstable, riddled with microscopic twists and tears that defy our everyday intuition. What's actually happening in this quantum frenzy? At scales a trillion times smaller than an atom, particles and their antimatter counterparts spontaneously blink into existence, only to annihilate each other an instant later. These aren't just theoretical quirks, they've been indirectly observed in lab experiments, proving that empty space is anything but empty. In fact, the vacuum of space is more like a boiling cauldron of energy, where virtual particles dance in and out of reality so fast we can't directly catch them in the act. This bizarre behavior isn't just a curiosity, it's the key to one of the most startling discoveries about black holes. Stephen Hawking realized that when these particle pairs pop up near a black hole's event horizon, something extraordinary happens. One particle might get sucked into the black hole while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over unimaginable stretches of time, this slow leak, now called Hawking radiation, means even the mightiest black holes evaporate, fading away into nothingness. The implications are staggering. If space-time is this unstable at its core, it challenges everything we think we know about the universe's structure. Some theories suggest these quantum fluctuations could even spawn tiny, short-lived wormholes, bridging distant points in space for fractions of a second. Others propose that the foam might hold clues to unifying gravity with quantum mechanics, a puzzle that stumped physicists for a century. And here's the real kicker. If quantum foam exists, it means the smooth, continuous universe we perceive is an illusion, a cosmic mirage hiding the frenetic, unpredictable truth beneath. Every second, trillions of these virtual particles flicker in and out of existence all around us, invisible yet shaping the very fabric of reality. It's a reminder that even in the quietest corners of space, nothing is ever truly still. The universe is unimaginably vast, with billions of habitable planets scattered across countless galaxies, so where is everybody? This haunting question lies at the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously pointed out the contradiction between the high probability of alien civilizations and our total lack of evidence for them. If life is so likely, why does space feel so empty? The answers range from chilling possibilities to surprisingly hopeful ones, and none of them leave us unchanged. One of the most unsettling explanations is the idea of great filters, cosmic hurdles so deadly they wipe out civilizations before they can spread across the stars. Think of it like a series of traps hidden in the path of evolution. Maybe the filter is behind us, something rare like the jump from simple cells to complex life, making us one of the lucky exceptions. Or worse, what if it's ahead of us, a future catastrophe like runaway AI or self-destructive technology that dooms every civilization before they can make contact? The chilling implication: if the filter is still in our future, we might be doomed before we ever leave our solar system. But there are brighter possibilities too. Some scientists argue we're simply early to the cosmic party. The universe is 13.8 billion years old, but it's only in the last few billion that conditions were right for life as we know it. Stars like our Sun are relatively young, and the raw materials for planets took eons to form. If civilizations tend to arise later in cosmic history, we might be among the first pioneers in a galaxy that hasn't yet awakened to its full potential. In this scenario, the silence isn't ominous, it's just a sign that we're ahead of the curve. Then there's the zoo hypothesis, the idea that advanced civilizations are out there but deliberately avoiding us, treating Earth like a nature preserve or a lab experiment. Imagine ants suddenly realizing humans exist. Would we bother explaining ourselves to them? Similarly, aliens might see us as too primitive, too fragile, or simply not worth the trouble. Or perhaps they communicate in ways we can't even perceive, using technologies beyond our comprehension. The truth is, the Fermi paradox isn't just about aliens. It holds up a mirror to humanity, forcing us to confront our own fragility and potential. Are we alone because life is incredibly rare, or because intelligence inevitably self-destructs? Are we the first, the last, or just one voice in a chorus we can't yet hear? Every possible answer reshapes how we see our place in the cosmos, turning the silence of space into one of the most profound mysteries we've ever faced. Back in 1977, a radio telescope in Ohio picked up something that sent chills down astronomers' spines. A signal so bizarre, so perfectly matched to what we'd expect from an alien transmission, that the scientist who discovered it scrawled, "Wow." In red ink right on the printout, that single burst of radio waves, lasting just 72 seconds, came from the direction of the Sagittarius constellation and carried all the hallmarks of an artificial broadcast. It was narrow, intense, and tuned to a frequency that hydrogen, the most common element in the universe, naturally emits, making it an ideal channel for interstellar communication. Decades later, we still don't know what caused it. Some argue it could have been a passing comet, reflecting sunlight in just the right way to mimic an artificial signal. But here's the problem. Comets don't emit strong radio waves at that specific frequency, and when researchers retraced the signal's origin years later, no known comet was anywhere near that patch of sky. Others suggest it might have been a bizarre astrophysical event, a star collapsing, a black hole burping, or some cosmic phenomenon we haven't even named yet. But nothing fits quite right. The most tantalizing possibility, that the WOW signal was exactly what it looked like, a fleeting hello from another civilization. Imagine the scenario. Somewhere out there, a distant planet's beacon flickered on just long enough for us to catch a whisper, then vanished before we could turn our telescopes back for a second listen. It's the ultimate cosmic tease, a message that might have held the answer to whether we're alone, slipping through our fingers before we could decode it. What makes the WOW signal so haunting isn't just its mystery, it's the way it exposes how unprepared we are for contact. Even if aliens were shouting our way, our telescopes are only pointed at the sky intermittently. It's like trying to catch a lightning bug in a pitch-black field with a flashlight that flickers on for a second every hour. We might have missed countless signals, or worse, heard one and dismissed it as noise. The search for an explanation continues, but one thing's certain: the WOW signal remains one of the universe's most tantalizing riddles. Whether it was a cosmic fluke or a deliberate ping from the stars, it's a reminder that space is full of surprises, and sometimes they're shouting right at us when we're barely listening. In the constellation Cygnus, there's a star that behaves like nothing else we've ever seen. KIC 8462852, better known as Tabby's star after the astronomer Tabitha Boyajian, who first flagged its bizarre activity, flickers and dims in ways that defy all conventional explanations. Most stars show tiny, rhythmic dips in brightness when planets pass in front of them, but Tabby's star doesn't play by those rules. Instead, it plunges by up to 22% at random intervals, as if something colossal and irregular is blocking its light. For a while, even scientists entertained the wild idea that we might be looking at an alien megastructure. The theory wasn't as far-fetched as it sounds. Imagine a civilization so advanced they've built a Dyson swarm, a vast network of solar panels encircling their star to harvest its energy. Such a structure would block starlight in unpredictable patterns, just like what we observed. The idea sent shockwaves through the astronomy community, but the truth turned out to be both stranger and more mundane. After years of scrutiny, the leading explanation isn't aliens, it's an enormous, uneven cloud of dust orbiting the star. Not just any dust, though. This stuff behaves unlike anything in our own solar system, clumping and dispersing in ways that still aren't fully understood. What makes Tabby's star truly remarkable isn't just its odd behavior, it's how the mystery unfolded. When professional astronomers were stumped, they turned to the public for help. Thousands of citizen scientists sifted through data, crowdfunded telescope time, and even monitored the star's flickers from their backyards. It was a testament to how modern astronomy isn't just done in ivory towers. It's a collaborative effort fueled by curiosity from people around the world. The case isn't entirely closed, though. While dust seems to be the culprit, no one knows where it came from or why it moves the way it does. Some speculate it's the aftermath of a catastrophic planetary collision, a cosmic traffic smash that left debris spiraling wildly. Others wonder if the star itself is unstable, sporadically belching out vast plumes of material. Each new observation peels back another layer, revealing just how little we truly know about the lives of stars, and how even the most outlandish theories can push science forward. Tabby's star reminds us that the universe is still full of surprises. Whether it's dust or something we haven't imagined yet, this flickering enigma proves that sometimes the most ordinary explanations can be just as thrilling as the wildest sci-fi scenarios. The search for answers continues, and every flicker of that distant sun pulls us deeper into the mystery. High above Earth, a shadowy object has sparked wild theories for decades, the so-called Black Knight satellite. Conspiracy claims describe it as a 13,000-year-old alien probe silently orbiting our planet, watching us. The legend grew from blurry photos, alleged radio signals, and even a supposed quote from Nikola Tesla about intercepting strange transmissions from space. But here's the twist: science has a far simpler explanation, one that doesn't involve ancient astronauts. The truth traces back to 1998, when astronauts aboard the Space Shuttle Endeavour were installing new parts on the International Space Station. During the mission, a thermal blanket accidentally floated away, a mundane piece of insulation lost to the void. Drifting in orbit, it caught sunlight at odd angles, creating the illusion of a dark, jagged object in grainy footage. NASA confirmed this years later, but by then, the myth had taken on a life of its own. So why does the myth persist? Part of it's the thrill of mystery. The idea of an alien artifact lurking just overhead taps into our love for cosmic secrets. But there's also a deeper pattern here: how easily human minds connect random dots into narratives. Before the thermal blanket, people misidentified everything from discarded rocket parts to space debris as the Black Knight. Even earlier, in the 1960s, unusual radar echoes from high-altitude ice crystals fed into the legend. Each time, science offered rational explanations, yet the story adapted, clinging to gaps in public knowledge. That said, the universe is strange enough without inventing myths. We've found actual interstellar objects like Oumuamua that pass through our solar system with no clear origin, and projects like SETI scan the skies daily for genuine alien signals. The real wonder isn't in fictional probes. It's in the tangible mysteries we're still unraveling, from rogue planets drifting between stars to the eerie fast radio bursts blasting across the cosmos. The Black Knight myth reminds us how easily folklore fills the void when facts feel too ordinary. But ironically, the truth is often more fascinating. That thermal blanket, it's a tiny speck in the vast theater of space exploration, proof that even our accidents become part of the cosmic story, floating alongside real wonders waiting to be discovered. The Moon today is a quiet, barren world with no magnetic field to shield it from the harsh solar wind. But buried in its ancient rocks lies a startling secret: it wasn't always this way. Billions of years ago, our lunar neighbor crackled with a magnetic force far stronger than Earth's, a protective bubble that vanished mysteriously, leaving behind only cryptic clues in moon dust. The evidence comes from Apollo mission samples chunks of lunar rock that locked tiny magnetic signatures into their crystals as they cooled. When scientists analyzed these fragments, they found something impossible: minerals aligned as if shaped by a magnetic field up to 100 times more powerful than Earth's current one. Picture the Moon not as the pale orb we know, but as a dynamic world with a molten, churning core, generating a magnetic shield robust enough to deflect cosmic radiation. So what killed this lunar powerhouse? The leading theory points to catastrophe in the Moon's molten heart. In its youth, the Moon's core was likely rich in radioactive elements like uranium and thorium, their decay providing the heat needed to drive a magnetic dynamo. But as those elements depleted and the core cooled, the dynamo sputtered out. Another possibility involves colossal impacts, early bombardments that shattered the Moon's internal structure, disrupting the delicate balance needed to sustain a magnetic field. Some models even suggest Earth's gravity played a role, tugging on the Moon's interior like an invisible hand squeezing a stress ball, draining its energy over time. The implications rewrite lunar history. A magnetic field would have sheltered the Moon's early atmosphere from being stripped by solar winds, potentially allowing water or even primitive chemistry to persist on its surface. It also raises tantalizing questions. Could other lifeless moons, like Mars' Phobos or Jupiter's Europa, have once pulsed with similar invisible shields? And if so, did those fields vanish for the same reasons? The Moon's magnetic past is a ghost story etched in stone, a reminder that even the most familiar objects in our sky were once wildly different. Its silent surface now hides the echoes of a time when it wasn't just Earth's companion, but a world with its own fiery heartbeat. Venus might look like Earth's serene twin from a distance, but up close, it's a world of atmospheric chaos. While the planet itself rotates painfully slow, taking 243 Earth days to complete a single spin, its atmosphere races around at 360 kilometers per hour, completing a full lap every 4 days. That's 60 times faster than the surface beneath it, a phenomenon so extreme scientists call it superrotation. Picture a colossal hurricane wrapping around the entire planet, never weakening, never stopping, a perpetual storm fueled by conditions unlike anything in our solar system. What drives this dizzying atmospheric sprint? The answer lies in a catastrophic feedback loop of heat and wind. Venus is shrouded in a thick blanket of carbon dioxide, with clouds of sulfuric acid trapping so much sunlight that surface temperatures soar to 460 degrees Celsius, hot enough to melt lead. This oven-like heat creates extreme pressure differences between the planet's day and night sides, even though a single Venusian day lasts nearly 117 Earth days. Those temperature contrasts whip the atmosphere into a frenzy, with winds accelerating as they redistribute heat across the globe. But there's another twist. Venus lacks the braking system Earth has. Our planet's mountains and oceans slow down atmospheric movement, creating a more balanced circulation. Venus, with its eerily smooth surface and no liquid water, offers no such resistance. The superrotation just builds momentum, like a runaway train with no tracks to slow it down. Even the sun's gravitational tug plays a role, its tidal forces further stirring the atmospheric pot in a process called thermal tides. The consequences are surreal. At the cloud tops where sunlight first strikes, hurricanes rage non-stop, while near the surface, the air is so dense it moves like syrup, creeping along at barely 5 kilometers per hour. This disconnect creates layers of wind shear so violent they could shred any spacecraft daring to linger. And because the atmosphere carries so much heat, the planet's surface barely experiences day-night temperature changes. just a constant, suffocating blanket of heat. Superrotation isn't just a curiosity, it's a warning. Studying Venus helps us understand how atmospheres evolve, especially under the grip of a runaway greenhouse effect. Some models suggest Earth could one day face similar extremes if climate change spirals out of control. Venus shows us what happens when a planet loses its balance, its skies becoming a relentless engine of wind and storm, forever racing against itself. Mars has been teasing us with one of the solar system's most frustrating mysteries: sudden, unexplained puffs of methane gas that appear and vanish without warning. The Curiosity rover has sniffed these elusive spikes multiple times since landing in 2012, detecting methane concentrations that briefly soar to 10 times background levels before disappearing just as fast. On Earth, methane is often a calling card of life, produced by everything from cows to microbes. So is Mars whispering hints of hidden biology beneath its rusty surface, or are we seeing the fingerprints of an entirely different process? The debate hinges on two competing explanations. The first involves geology specifically, a reaction called serpentinization. When water seeps through certain mineral-rich rocks like olivine, it can trigger chemical reactions that release methane as a byproduct. Mars has plenty of these minerals, and if liquid water still lurks underground in isolated pockets, it could be fueling this slow, steady gas production. The methane might then seep to the surface through cracks, building up in pockets that occasionally burst open when conditions are right. But here's where it gets weird. If serpentinization were the sole source, methane levels should follow predictable patterns higher near geological hotspots, for instance, or varying with the seasons. Instead, Curiosity's data shows erratic spikes that defy easy explanation. Some scientists argue this volatility points to something more exciting: microbes. On Earth, certain hardy bacteria thrive deep underground without oxygen, metabolizing hydrogen and carbon dioxide to produce methane. If similar organisms exist on Mars, perhaps clinging to life in briny, subglacial reservoirs, their intermittent activity could explain the rover's unpredictable readings. There's another twist. Europe's Trace Gas Orbiter, a spacecraft designed specifically to study Martian methane from orbit, has repeatedly failed to confirm Curiosity's ground-level detections. This discrepancy could mean the methane is incredibly localized, dissipating too quickly for orbiters to spot. Or it might hint at an even stranger possibility, that the methane isn't coming from below at all, but from the rover itself. Some engineers speculate that ultra-tiny amounts of terrestrial methane, hitchhiking from Earth inside Curiosity's instruments, could be leaking out during temperature swings, creating false signals. The stakes couldn't be higher. If the methane is biological, it would be the strongest evidence yet that life isn't confined to Earth. But if it's geological, it still rewrites our understanding of Mars as a dead world, revealing an active, chemically complex interior. Every new detection and every frustrating absence adds another layer to the puzzle, proving that even a planet as seemingly barren as Mars still has secrets to share. Until we dig deeper, either with future rovers or human boots on the ground, these tantalizing whiffs of gas will keep us guessing. Beneath the icy crust of Jupiter's moon Europa lies an ocean unlike any other in our solar system. A vast global sea of liquid saltwater stretching over 100 kilometers deep. That's more than 10 times the depth of Earth's Mariana Trench, hidden under a shell of ice just a few kilometers thick in places. What makes this ocean truly extraordinary isn't just its existence, but what powers it: the relentless gravitational tug of war between Europa, Jupiter, and its neighboring moons. Every time Europa orbits Jupiter, the gas giant's immense gravity squeezes and stretches the moon like putty, generating enough internal heat to keep that subsurface ocean liquid despite the freezing void of space. This isn't some stagnant, dead body of water. Europa's ocean is almost certainly active, with hydrothermal vents churning on its seafloor, just like those in Earth's deepest oceans, where scalding mineral-rich water fuels thriving ecosystems completely cut off from sunlight. On Europa, these vents could be mixing essential chemicals into the water, creating the perfect cocktail for life to emerge. Scientists have even detected plumes of water vapor erupting through cracks in the ice, shooting hundreds of kilometers into space, direct evidence that the ocean isn't just trapped down there, but interacting with the surface and potentially spewing its contents into the cosmos. The parallels to Earth are impossible to ignore. Life here clings to even the harshest environments, from acidic hot springs to crushing ocean trenches. If organisms can survive in those extremes, why not in Europa's dark, salty abyss? The Moon's ice shell likely shields the ocean from Jupiter's lethal radiation, while tidal heating provides a steady energy source, no sunlight required. Some researchers speculate that Europa's ocean floor could host entire food webs, with microbes feeding on chemical reactions near vents and larger organisms grazing on them. But the real kicker, Europa isn't alone. At least two other Jovian moons, Ganymede and Callisto, are suspected to harbor subsurface oceans, and Saturn's Enceladus shoots its own geysers into space. Yet Europa remains the crown jewel, with the right mix of water, heat, and chemistry to make it the solar system's prime candidate for alien life. Future missions like NASA Europa Clipper aim to fly through those plumes, analyzing their contents for organic molecules or even cellular remnants. What's at stake isn't just finding microbes on another world, it's rewriting the story of life itself. If Europa's ocean holds even simple organisms, it would prove that life isn't a fluke confined to Earth, but a cosmic imperative bubbling up wherever conditions allow. That tiny, ice-covered moon could hold the answer to one of humanity's oldest questions. Are we alone? And the ocean silently waiting beneath its frozen surface might just whisper back. Imagine a planet where the skies rain diamonds not as glittering stones, but as molten, liquid gems that fall from clouds of carbon vapor. This isn't science fiction. It's the reality of 55 Cancri, a bizarre world orbiting a star 40 light-years away. Twice the size of Earth, but nearly 8 times as massive, this planet's composition reads like something from an alchemist's dream. A third of its mass could be pure carbon, compressed under such insane pressure that it crystallizes into diamond. Here's how it works. Under normal circumstances, carbon turns to diamond deep within a planet's mantle, where crushing pressures force atoms into that iconic crystalline structure. But 55 Cancri takes this process to apocalyptic extremes. Temperatures on its surface soar above 2,000 degrees Celsius, hot enough to melt iron, while the atmospheric pressure is hundreds of thousands of times greater than Earth. These conditions don't just create diamonds, they turn the planet into a factory for surreal carbon chemistry. Scientists believe the planet's crust might be a tangled mess of graphite and diamond, with vast oceans of molten carbon stretching across its surface. The real spectacle happens higher up, where carbon-rich vapor in the atmosphere could condense into diamond raindrops under the relentless pressure. Picture a storm where instead of water, droplets of liquefied diamond streak through searing hot skies, only to vaporize again as they fall into the planet's molten layers. But there's a twist. Unlike Earth's diamond-forming processes, which take billions of years, 55 Cancri's entire carbon cycle could be turbocharged by its extreme environment. Some models suggest tidal forces from its parent star keep the planet's interior churning violently, constantly recycling carbon between the surface and atmosphere. It's a world where geology moves at the speed of weather, with diamond formation happening not over eons but in real time. The catch: we can't mine this glittering hellscape. Even if we could reach it, the surface would crush and vaporize any probe within seconds. But studying 55 Cancri E teaches us something profound. The universe crafts materials in ways we'd never see on Earth. If a planet can turn carbon into raining diamonds, what other impossible chemistry is lurking out there in the dark? Most stars live relatively quiet lives, orbiting peacefully around their galaxy's center. But some are cosmic outlaws hurled into the void at mind-bending speeds by forces beyond imagination. These are hypervelocity stars, stellar fugitives racing through space at over 1 million miles per hour, fast enough to cross the entire United States in less than 2 seconds. Their origin story reads like an interstellar crime thriller, with supermassive black holes playing the role of the ultimate slingshot. Picture a binary star system, 2 stars locked in a graceful dance, wandering too close to the monster lurking at the galaxy's heart. The black hole's overwhelming gravity captures one star while violently ejecting the other, flinging it outward like a stone from a catapult. This cosmic game of gravitational pinball doesn't just give the star a gentle nudge, it sends the survivor rocketing away at up to 5,000 kilometers per second, fast enough to escape the galaxy entirely. Astronomers have tracked dozens of these runaway stars blazing across intergalactic space, their trajectories marking an invisible highway of stellar escapees. One of the most dramatic examples is Zeta Ophiuchi, a blue giant plowing through space at 80,000 kilometers per hour, so fast it's creating a visible shockwave in the cosmic dust ahead of it. Infrared images reveal a dramatic bow shock wrapping around the star, like the wake of a speedboat cutting through still water. The sheer force of its passage heats surrounding gas to millions of degrees, creating a glowing, arc-shaped ripple visible across light years. What makes Zeta Ophiuchi particularly fascinating is that it wasn't simply ejected. It was likely launched by a supernova explosion that obliterated its former companion star, receiving an extra kick from the dying star's final moments. These hypervelocity stars do more than just paint dramatic pictures. They serve as cosmic probes. By tracing their paths backward, astronomers can map the gravitational landscape of our galaxy, including the distribution of invisible dark matter. Some hypervelocity stars even carry clues about conditions at the very heart of the Milky Way, preserving information about our black holes' feeding habits over millions of years. The universe has countless ways to surprise us, and hypervelocity stars are a perfect example. Celestial bodies turned into interstellar bullets, carrying their stories across the cosmos at impossible speeds. Each one we discover adds another piece to the puzzle of how galaxies evolve, and what happens when stars dare to venture too close to the darkness at their centers. Buried in the afterglow of the Big Bang lies a cosmic anomaly so vast it defies easy explanation: the cold spot. This eerie region, spanning a staggering 1.8 billion light-years across, shows up in the cosmic microwave background as a patch of space slightly cooler than its surroundings. It's not just a small fluctuation. The temperature difference is significant enough that scientists initially wondered if their instruments were malfunctioning. But repeated observations confirmed it was real, a colossal dent in the fabric of the universe, begging the question, what could possibly leave a mark that big? One of the most mind-bending theories suggests the cold spot might be a bruise left by a collision with another universe. According to some models of multiverse theory, our universe isn't alone. It's one bubble in an endless cosmic foam, where other universes with different physical laws might be floating just beyond our perception. If one of those bubbles brushed against ours in the distant past, the energy released could have created this massive cold region, like a fingerprint pressed into the afterglow of creation. It's a tantalizing idea, but there's a catch. No direct evidence proves other universes exist, making this explanation as speculative as it is thrilling. Skeptics argue the cold spot could be something far more mundane: a cosmic void, an enormous region of space where galaxies are unusually sparse. Voids aren't uncommon, but one this size would be extreme. When light travels through such a vast emptiness, it loses energy, stretching into longer, cooler wavelengths, an effect called the integrated Sachs-Wolf effect. The problem, even the largest known voids don't come close to explaining the cold spot scale. That leaves researchers scratching their heads. If it's not a void and not another universe, what then? Then there's the wild card. What if it's neither? Some theorists propose the cold spot could be a glitch in the data, an artifact of how we map the cosmic microwave background. Others wonder if it's evidence of exotic physics, a sign that dark energy behaves differently on massive scales, or that the early universe underwent phases we don't yet understand. The truth is, the cold spot doesn't fit neatly into any existing box. It's a cosmic outlier, challenging us to rethink what we know about the universe's structure. What makes this mystery so compelling isn't just the science, it's the stakes. If the cold spot really is evidence of a multiverse, it would revolutionize our understanding of reality itself. But even if it's something more ordinary, its sheer size forces us to confront how little we grasp about the universe's largest structures. It's a reminder that the cosmos still holds puzzles too big to ignore, and that sometimes the coldest spots in the sky burn the hottest with unanswered questions. Your phone's GPS works with eerie precision, guiding you to the right street corner, the perfect parking spot, even the exact picnic table in a crowded park. But here's something that might blow your mind. Without accounting for Einstein's theory of relativity, those directions would be wrong by nearly 7 miles every single day. That's because time itself ticks differently up in orbit than it does down here on Earth, and if we didn't adjust for it, the entire global positioning system would unravel in real time. This bizarre effect stems from two key predictions of Einstein's relativity. First, special relativity tells us that the faster you move through space, the slower time passes for you relative to someone standing still. GPS satellites zip around Earth at about 14,000 kilometers per hour, which means their onboard clocks actually lag behind ground-based clocks by about 7 microseconds per day. But there's a twist. General relativity says time also speeds up in weaker gravitational fields. Since satellites orbit 20,000 kilometers above Earth's surface, where gravity is slightly weaker, their clocks gain about 45 microseconds per day. Combine these two effects and you get a net gain of roughly 38 microseconds daily. Sounds tiny, right? Here's why it matters. GPS relies on ultra-precise timing to calculate your position. Each satellite constantly broadcasts signals stamped with the exact time they were sent. Your phone compares those timestamps to figure out how far away each satellite is, then triangulates your location. But light travels at 300,000 kilometers per second, meaning a microsecond error in timing translates to 300 meters of positioning error on the ground. Over a single day, those unadjusted relativistic effects would snowball, throwing off your location by kilometers. The system would become useless within hours. To fix this, engineers pre-program the satellite's atomic clocks to tick slightly slower before launch, compensating for the relativistic effects in advance. It's like setting a watch to run fast knowing it'll slow down during a race. Without this correction, the entire GPS network would drift by roughly 10 kilometers per day, turning your morning commute into a guessing game and making aerial navigation dangerously unreliable. The craziest part, this isn't some abstract physics experiment, it's proof that relativity shapes our daily lives in tangible ways. Every time you check a map or order a rideshare, you're relying on century-old insights about the fabric of spacetime. Einstein's equations aren't just scribbles on a chalkboard, they're the invisible hands keeping our modern world synchronized, one corrected microsecond at a time. Deep in the cosmos, some of the universe's most violent tantrums unfold on the surface of tiny, ultra-dense stellar corpses, neutron stars. These city-sized remnants of supernova explosions pack more mass than our sun into a sphere barely 20 kilometers across, creating gravitational forces so intense that a single sugar cube-sized chunk would weigh as much as a mountain. But even these bizarre objects have their breaking points. When their crusts crack under unimaginable pressure, the resulting starquakes unleash energy equivalent to the sun's entire output for 100,000 years, all in less time than it takes to blink. The physics behind these cosmic convulsions is as extreme as the stars themselves. Neutron star crusts are a lattice of atomic nuclei squeezed so tightly that electrons merge with protons, forming a bizarre, ultra-rigid material sometimes called nuclear pasta. Picture the surface as a thin shell of crystalline neutron matter, floating atop an ocean of fluid neutrons like an eggshell stretched over a bowling ball. As the star spins, intense magnetic fields twist this crust, building up stress until it suddenly fractures. The recoil sends shockwaves rippling through the star, triggering oscillations that make the entire object ring like a bell while firing beams of X-rays and gamma rays into space. One of the most dramatic examples happened in 2004, when a neutron star 20,000 light-years away released a starquake so powerful it briefly outshone the full moon in gamma rays despite being halfway across the galaxy. Satellites detected the burst as a sudden spike in radiation, and when scientists analyzed the data, they realized the quake had permanently altered the star's shape, causing its rotation to hiccup by 300 microseconds. That might not sound like much, but for an object spinning hundreds of times per second, it's the equivalent of slamming on cosmic brakes. What makes these events truly mind-bending is how they warp space-time itself. The energy released is enough to send gravitational waves rippling across the universe, distortions in the fabric of reality predicted by Einstein and finally detected a century later. Starquakes might even solve a long-standing mystery: why some neutron stars occasionally glitch, suddenly speeding up their rotation. The leading theory suggests these glitches occur when the quake shockwaves reach the star's interior, momentarily unlocking superfluid neutrons that had been pinned in place, unleashing a surge of angular momentum like a spinning ice skater pulling in their arms. These catastrophic tremors aren't just cosmic curiosities, they're extreme physics labs. By studying the X-ray pulses and gravitational echoes of starquakes, scientists probe matter under conditions impossible to recreate on Earth, testing theories about how particles behave at densities where even atoms collapse. Every time a neutron star's crust snaps, it sends us a message from the edge of physical possibility, written in the language of space-time itself. And each one reminds us that even in death, stars have ways of making their presence violently known. Far beyond the last planet, past the rocky belt of Pluto and the icy reach of Neptune, lies a vast, invisible reservoir of frozen wanderers, the Oort cloud. This colossal shell of icy debris stretches nearly a light-year from the Sun, marking the final frontier where our star's gravitational grip grows so weak that even the slightest nudge can send its inhabitants tumbling into the void of interstellar space. Imagine a cosmic freezer packed with trillions of ancient comets, each one a pristine relic from the solar system's birth, waiting in the dark for a chance to blaze across our skies. What's astonishing isn't just the scale of this frozen archive, it's how little we know about it. Unlike the asteroid belt or Kuiper belt, the Oort cloud isn't something we can photograph or probe. Its existence is inferred from the orbits of long-period comets, those rare, dazzling visitors that take thousands, sometimes millions, of years to swing by the Sun. When these icy travelers appear, like the famous Hale-Bopp comet in 1997, they're often fresh from the Oort cloud, carrying unchanged chemistry from the solar system's infancy. The structure itself is a cosmic marvel, not a flat ring, but a spherical bubble encasing our entire solar system. Picture a swarm of icebergs adrift in the darkest ocean, so sparsely scattered that a spacecraft could fly through without spotting a single one. Yet collectively, they hold enough mass to dwarf the inner planets. Some estimates suggest the Oort cloud could contain up to 20 times the mass of Earth, locked away in a deep freeze colder than anything our probes have ever measured. Here's where it gets eerie. The Oort cloud isn't just a passive storage unit, it's a celestial firing range. Passing stars, rogue planets, or even the Milky Way's tidal forces can jostle these comets, sending them careening inward toward the Sun. That's likely how we got comets like Halley or the spectacular Great Comet of 1843, but occasionally something far more dramatic happens. When a star drifts unusually close like Gliese 710, which will pass within just 1 light year of us in about 1.3 million years, it could trigger a comet storm, flinging thousands of these icy fragments into the inner solar system. Some scientists speculate that such an event might have played a role in Earth's ancient mass extinctions. Yet for all its mystery, the Oort cloud holds clues to our origins. These comets are time capsules, preserving ices and organic molecules untouched for 4.5 billion years. Some may even contain material older than the Sun itself, borrowed from the interstellar cloud that birthed our solar system. Missions like the European Space Agency's Comet Interceptor aim to visit one of these pristine objects, hoping to decode secrets about how water, and perhaps even life's building blocks, arrived on Earth. The Oort cloud is more than a distant curiosity. It's the solar system's silent sentinel, a reminder of how small our neighborhood really is. Its icy residents rarely visit, but when they do, they bring with them stories from the edge of oblivion, and proof that even in the darkest corners of space, the universe is anything but still. In the 1970s, NASA Pioneer probes became cosmic mysteries themselves, not for what they found, but for how they moved. These twin spacecraft, the first to journey beyond Mars and Jupiter, were meticulously tracked by scientists expecting their trajectories to follow the cold, precise laws of gravity. But something was off. By the 1980s, researchers noticed both probes were slowing down ever so slightly, as if an invisible hand were gently tugging them backward. The discrepancy was tiny, just 300 miles off course over a decade, but in the unforgiving vacuum of space, where every calculation is razor sharp, even that minuscule anomaly sent shockwaves through the scientific community. At first, theories ranged from the dramatic to the downright wild. Could it be a flaw in our understanding of gravity itself? Some speculated about dark matter dragging on the probes, or even undiscovered physics altering their path. The anomaly became known as the Pioneer Effect, a puzzle that lingered for decades, fueling debates and inspiring countless research papers. Then, in 2012, the answer finally arrived, and it was surprisingly ordinary. After painstakingly reconstructing the probe's designs, engineers realized the culprit wasn't cosmic at all. It was heat. The radioactive generators powering the spacecraft were emitting infrared radiation unevenly, creating a subtle but constant push in the opposite direction. Like a car idling with one brake slightly engaged, that thermal recoil was enough to slow the Pioneers bit by bit over billions of miles. But don't let this mundane explanation fool you. Spacecraft anomalies are far from solved. Even today, missions like NASA's Juno orbiter experience unexplained shifts in velocity as they navigate the solar system. Some scientists suspect these glitches could hint at deeper mysteries, like variations in the Sun's gravitational influence or the faint pressure of interstellar gas. Others wonder if there's still room for new physics to reveal itself in the quiet drift of humanity's farthest-flung machines. The Pioneer anomaly reminds us that space exploration is full of surprises, where even the smallest hiccup can lead to years of head-scratching. Sometimes the answers are simpler than we imagine. Other times they're waiting just beyond our reach, whispering that the universe still has tricks up its sleeve. The universe is expanding, that much we know for sure, but how fast? That's where things get messy. For decades, scientists have been locked in a heated debate over conflicting measurements of the cosmos expansion rate, a puzzle so stubborn it's earned a dramatic name, the Hubble Tension. On one side, we have observations of the early universe, specifically the cosmic microwave background suggesting a relatively sedate expansion rate. On the other, measurements of nearby stars and supernovas point to a universe that's stretching faster, as if something's giving it an extra push. The discrepancy isn't just a rounding error. It's a gap big enough to hint that our understanding of physics might be missing a crucial piece. Here's why it matters. The cosmic microwave background, often called the universe's baby picture, captures light from just 380,000 years after the Big Bang. By studying its ripples, scientists can calculate how fast the universe was expanding back then extrapolate forward using our best models of dark energy and gravity. That method gives us one number, call it the early universe rate. But when astronomers measure the present-day expansion by tracking the distances and speeds of galaxies, they get a value nearly 10% higher. That's like two clocks, both built by the same master watchmaker, ticking out of sync for no apparent reason. The most exciting possibility: new physics. Maybe dark energy isn't constant but evolves over time, growing stronger and accelerating the universe faster than predicted. Or perhaps dark matter interacts with itself in ways we haven't accounted for, subtly altering the cosmic tug-of-war between expansion and gravity. Some theorists have even floated the idea of an undiscovered particle, a dark radiation, that flooded the early universe, leaving traces in today's expansion rate. These aren't wild guesses, they're serious proposals, each with implications that could rewrite textbooks. But before we toss out our models, there's another option: human error. Measuring cosmic distances is notoriously tricky. The distance ladder, the series of techniques used to gauge how far away galaxies are, relies on overlapping methods, each with its own uncertainties. A tiny misstep in calibrating supernova brightness or interpreting the flicker of variable stars could throw everything off. Even the Hubble Space Telescope, our most precise tool for this work, has limitations. Could the tension just be a cascade of small mistakes magnified across billions of light years? The stakes couldn't be higher. If the discrepancy is real, it means our universe is stranger than we thought, governed by forces we've yet to uncover. If it's an error, it exposes cracks in the foundations of modern astronomy. Either way, the Hubble tension isn't just a technical hiccup. It's a cosmic wake-up call, reminding us that the universe still holds cards close to its chest. Every new observation, from next-generation telescopes to refined calculations, brings us closer to an answer, and when we find it, we might just discover that the real mystery was only beginning. Beyond Neptune's orbit, the Kuiper belt isn't just a graveyard of icy leftovers, it's a cosmic crime scene, and the evidence points to a missing suspect. Some of its most distant objects, like the dwarf planet nicknamed the Goblin, follow such bizarre, elongated orbits that astronomers are convinced something massive must be tugging on them from the shadows. These frozen wanderers don't just drift randomly, their paths cluster in ways that defy chance, as if an invisible hand were herding them. The math suggests only one thing could explain this pattern: a hidden world, possibly 10 times Earth's mass, lurking in the frozen darkness. Welcome to the hunt for Planet 9. What makes these oddball Kuiper belt objects, or KBO, so suspicious? Take Sedna, for example, a dwarf planet with an orbit so stretched out that its closest approach to the Sun is still farther than Neptune, while its farthest point takes it 76 times that distance into the void. Then there's the Goblin, officially labeled 2015 TG 387, which takes 40,000 years to complete a single lap around the Sun, its path tilted at an angle that makes it stick out like a sore thumb among its neighbors. These orbits aren't just unusual, they're statistically improbable unless something massive is warping their trajectories over millennia. Enter Planet 9. In 2016, astronomers Konstantin Batygin and Mike Brown crunched the numbers and found that the peculiar clustering of these distant KBOs could only be explained by the gravitational pull of an undiscovered super-Earth. Picture a hidden giant orbiting the Sun once every 10 to 20,000 years, so far out that it's never caught sunlight's reflection. Its influence wouldn't just nudge objects like the Goblin, it would sculpt their orbits over eons, herding them into a cosmic fingerprint that mathematicians can trace. But here's where the mystery deepens. If Planet 9 exists, why haven't we spotted it yet? The answer lies in the challenges of observing such a distant, dim world. At its hypothesized distance, sunlight would be thousands of times fainter than on Pluto, making it virtually invisible to all but the most sensitive telescopes. Even worse, its orbit could take it through the densest part of the Milky Way's starfield, camouflaging it against a backdrop of twinkling stars. Detectives in this cosmic manhunt are turning to every tool available. The Subaru telescope in Hawaii scans vast swaths of sky, while algorithms sift through old survey data for overlooked clues. Some researchers even suggest Planet 9 might not be a traditional planet at all. It could be a primordial black hole, no larger than a grapefruit but with the mass of a world warping space around it. Others propose it was an exiled rogue planet captured by the Sun's gravity long ago. Whether or not Planet 9 is ever found, these weird KBO orbits have already rewritten the textbook on our solar system's edges. They remind us that even in our own cosmic backyard, there are still uncharted territories, and perhaps giants hiding in the dark waiting to be discovered. Our Milky Way isn't the serene cosmic island it appears to be. It's a predator currently devouring a smaller galaxy in plain sight. The Sagittarius dwarf spheroidal galaxy, a faint smudge of stars 10,000 times lighter than our own, is being torn apart strand by strand, its stars slowly swallowed into the Milky Way's spiral arms. This isn't some ancient event lost to time. It's happening right now, a slow-motion feast that astronomers have watched unfold over the last 2 decades. Here's how galactic cannibalism works. Gravity doesn't play favorites when a smaller galaxy wanders too close to a larger one. The bigger galaxy's tidal forces stretch and shred it like cosmic taffy. Sagittarius dwarf first crossed paths with the Milky Way around 6 billion years ago, and each time it loops back on its elongated orbit, our galaxy strips away another layer of its stars. Telescopes have mapped these stolen stars in eerie detail, tracing streams of them wrapped around the Milky Way like ribbons. One trail, called the Sagittarius Stream, arcs over the night sky from Aquarius to Ursa Major, celestial breadcrumbs marking the dwarf galaxy's demise. But the Milky Way's appetite won't stop there. In about 4 billion years, we're set for the ultimate cosmic collision, a head-on merger with the Andromeda Galaxy. Simulations show the two spirals approaching at 400,000 kilometers per hour, their gravitational pull warping each other's shapes into chaotic stellar firework displays. For over 1 billion years, they'll dance closer, flinging stars out of their orbits and igniting bursts of new star formation before finally settling into a single, giant elliptical galaxy. What's wild is how little this apocalypse will affect our solar system. The space between stars is so vast that even when galaxies collide, actual stellar collisions are vanishingly rare. Earth's night sky, though, will transform into something unrecognizable. Andromeda's spiral arms swelling from a faint smudge into a blazing disk, then fracturing into streaks of light as tidal forces rewrite the heavens. By the merger's end, the Milky Way as we know it will be gone, replaced by a new hybrid galaxy some astronomers have nicknamed Milkdromeda. This violent ballet isn't unique. Galaxies grow by consuming smaller neighbors, and the universe's largest galaxies owe their size to eons of celestial mergers. Even our own Milky Way bears scars from past meals. Studies suggest its outer halo is littered with stars stolen from dwarf galaxies long ago digested. The cosmos operates on a scale of time and force we can scarcely comprehend, where galaxies rise and fall like empires, their histories written in the stars they've consumed. And somewhere in that future merger's glow, perhaps another civilization will look up and wonder about the giants that came before. our Sun may have once had a violent twin, a dark companion lurking at the edge of our solar system, occasionally stirring up cosmic chaos. This hypothetical star, nicknamed Nemesis, could explain one of Earth's greatest mysteries: why mass extinctions like the dinosaurs' demise seem to follow a grim timetable. Every 26 million years or so, our planet's fossil record shows catastrophic die-offs, as if something out there is flipping a cosmic kill switch. Here's how the theory works. Most stars are born in clusters, and our Sun likely had at least one sibling in its stellar nursery 4.6 billion years ago. Over time, gravitational tugs from passing stars and gas clouds scattered these siblings across the galaxy. But what if one stayed close? Nemesis would be a dim red dwarf or brown dwarf, orbiting far beyond the Oort cloud in a stretched elliptical path. Every time it swung back toward the inner solar system, its gravity would jostle the icy comets there, sending a lethal shower hurtling toward Earth. The evidence isn't just in the extinction cycles. Astronomers have noticed oddities in the orbits of distant objects like Sedna, which move as if tugged by something massive. While no direct trace of Nemesis has been found, surveys like NASA's WISE telescope have ruled out anything Jupiter-sized or larger within a certain range. That leaves room for a smaller, cooler star, or even a stealthy black hole, to hide in the data gaps. Skeptics argue that extinction patterns might just be statistical flukes, or that other cosmic events like the solar system's periodic passage through the Milky Way's dense spiral arms could trigger comet storms without needing a stellar culprit. But the allure of Nemesis persists because it solves multiple puzzles at once. Not only would it explain the timing of Earth's disasters, but its gravitational fingerprint might also account for the strange, clustered orbits of extreme trans-Neptunian objects. Whether or not Nemesis exists, the search has reshaped how we see our solar system's history. It reminds us that even familiar skies might hold forgotten siblings, dark, distant, and capable of reaching across the eons to remind us how fragile life really is. The cosmic microwave background, the faint afterglow of the Big Bang, should be the universe's most democratic feature, a near-perfect snapshot of uniformity. But when scientists mapped its subtle temperature variations, they stumbled on something unsettling: an eerie asymmetry nicknamed the axis of evil. This strange pattern reveals that one half of the universe appears slightly warmer than the other, while the other half aligns along a peculiar axis as if the cosmos itself were tilted. It's a deviation so statistically improbable that some researchers wonder if it's a crack in the foundation of modern cosmology. At the heart of the mystery is what the axis of evil implies about our place in the universe. According to the foundational cosmological principle, no location or direction should be special. The universe ought to look roughly the same everywhere when viewed on large scales. Yet the CMB's lopsided warmth and alignment seem to violate this rule, hinting that we might be sitting near the center of a structure that defies our understanding. Imagine drawing a line through space where temperatures subtly shift and galaxies align along invisible threads like iron filings around a magnet. If this isn't just a fluke, it could mean the universe isn't as homogeneous as we thought, or worse, that our assumptions about the Big Bang are missing something fundamental. Skeptics argue the anomaly might just be statistical noise, an illusion created by the way we process CMB data. After all, even random distributions can produce odd-looking patterns if you stare long enough. But the axis of evil stubbornly resists dismissal. When the Planck satellite refined earlier measurements in 2013, the asymmetry persisted, ruling out many instrumental errors. Alternative explanations range from the mundane, like residual contamination from our own Milky Way's dust, to the extraordinary, including theories that our universe collided with another bubble universe in the distant past, leaving a gravitational bruise imprinted on the CMB. The most radical possibility, that the axis of evil is evidence of a pre-Big Bang structure, a fingerprint from whatever existed before space-time as we know it began. Some models of quantum gravity suggest that the universe might have inherited anisotropic properties from an earlier phase, like wrinkles in fabric passed down from an unseen fold. Others propose that dark energy, the mysterious force accelerating cosmic expansion, might not be uniform after all, but clustered in ways that warp the large-scale structure of reality. What makes this cosmic oddity so compelling isn't just the science, it's the philosophical stakes. If the universe truly has a preferred axis, it undermines centuries of assumptions about cosmic humility, the idea that we occupy no special place in the grand scheme. Whether a measurement glitch or a paradigm-shifting clue, the axis of evil forces us to confront an uncomfortable truth. The deeper we peer into the cosmos, the more it seems to whisper that we've only just begun to unravel its secrets. Einstein famously called it spooky action at a distance, the bizarre quantum phenomenon where two particles become so deeply linked that manipulating one instantly affects its partner, no matter how far apart they are. This connection, known as quantum entanglement, defies our everyday intuition about how the universe should work. But in 2017, China's Misha satellite proved this cosmic magic trick isn't just laboratory sleight of hand. It operates flawlessly across staggering interstellar distances. The experiment was as elegant as it was groundbreaking. Scientists on Earth generated pairs of entangled photons, light particles whose quantum states were inseparably intertwined. They then beamed one photon from each pair up to Misha's as it hurtled overhead at nearly 5 miles per second, while keeping its entangled twin on the ground. Despite the satellite being 745 miles away, nearly the distance from New York to Chicago, measuring one photon's polarization state, still instantly determined its twin's behavior. This wasn't just a record-breaking achievement. It shattered assumptions about how fragile quantum links could be in the chaotic environment of space. What makes this cosmic entanglement so revolutionary is how it bypasses the speed of light. In our normal universe, nothing travels faster than light. It's the universe's ultimate speed limit. But entangled particles seem to coordinate instantaneously, as if space doesn't exist between them. Einstein hated this idea, calling it spooky, because it appeared to violate relativity's core principles. Yet Misha showed this spookiness survives Earth's atmosphere, radiation belts, and gravitational warping, real-world conditions where theorists feared decoherence might break the quantum spell. The practical implications are staggering. Entanglement could form the backbone of unhackable quantum internet, where information is teleported between satellites and ground stations with perfect security. Any attempt to eavesdrop would disturb the delicate quantum states, alerting communicators instantly. Misha itself demonstrated this by performing the first quantum-secured video call between Beijing and Vienna, encrypted using entangled keys generated across continents. But the experiment also revealed surprises. While entanglement held firm across vast distances, the act of transmitting photons through turbulent air introduced errors. Scientists had to develop ultra-sensitive detectors and precision tracking systems to compensate, like trying to thread a cosmic needle while riding a roller coaster. These technical hurdles prove that while nature allows this quantum weirdness, harnessing it at scale will push engineering to its limits. Perhaps most mind-bending is what this means for our understanding of reality. Quantum entanglement suggests that at some fundamental level, separateness might be an illusion, that the universe is profoundly interconnected in ways we're only beginning to glimpse. Every time Misha's photons defied classical physics across hundreds of miles, they whispered a tantalizing possibility that the true fabric of reality might be far stranger and far more beautifully linked than Einstein ever dreamed. For decades, scientists theorized that the first molecular bond in the universe wasn't water, carbon dioxide, or even simple hydrogen. It was an obscure mashup of hydrogen and helium called helium hydride. This fragile molecule, scrawled as He in chemistry textbooks, was predicted to form just moments after the Big Bang, when the searing hot cosmos cooled enough for electrons to latch onto nuclei. But despite its pivotal role in cosmic history, helium hydride remained frustratingly elusive until astronomers finally trapped its fingerprint in the swirling gases of a planetary nebula 3,000 light-years away. The discovery was a triumph of persistence. Helium hydride is notoriously unstable on Earth, surviving only in lab conditions that mimic the early universe's extreme environment. Out in space, its signal hides in a crowded neighborhood of the electromagnetic spectrum, drowned out by stronger emissions from molecules like carbon monoxide. But in 2019, NASA airborne SOFIA Observatory, a telescope mounted inside a modified Boeing 747, spotted its telltale infrared signature in the dying star's nebula NGC 7027. The detection wasn't just a cosmic scavenger hunt solved, it was a direct glimpse into the universe's chemical infancy. Here's why this molecule matters. In the first 100,000 years after the Big Bang, the universe was too hot for atoms to bond. Protons and electrons zipped around as a scorching plasma, blindingly opaque to light. But as expansion cooled the cosmos, helium, the second most abundant element, finally shared its electrons with lone hydrogen ions, forming the universe's first molecular handshake. These fragile helium hydride molecules then catalyzed the formation of molecular hydrogen, which became the building blocks for the first stars. Without that initial chemical spark, the cosmos might have remained a dark, sterile sea of disconnected atoms. The nebula where scientists found helium hydride offers a surprising parallel to those primordial conditions. NGC 7027 is a stellar graveyard, its ultraviolet radiation blasting apart molecules in ways that mimic the violent early universe. By confirming helium hydride's presence there, researchers effectively recreated a snapshot of chemistry's first trembling steps. It's like finding a fossilized footprint from the moment life learned to walk, except this imprint was forged not in mud, but in the aftermath of creation itself. What's even more astonishing is how long the search took. Though helium hydride was synthesized in labs as far back as 1925, spotting it in nature required waiting for telescope technology to catch up with theory. SOFIA's unique vantage point above 99% of Earth's infrared blocking water vapor gave it the precision to isolate helium hydride's faint signal from the nebula's molecular chatter. The discovery closes a century-old chapter in astrophysics while opening new questions. How widely did this molecule spread in the early universe, and could its remnants still linger in deep space today? This unassuming molecule story is a reminder that the universe's grandest narratives often hinge on the tiniest details. From the first fragile bond between helium and hydrogen sprang all the chemistry that built galaxies, stars, and eventually us. Every carbon atom in your body, every oxygen molecule you breathe, traces back to that initial spark, a whisper of structure emerging from chaos, now echoing across 13.8 billion years. Black holes aren't just cosmic vacuum cleaners, they're existential riddles wrapped in event horizons. At first glance, they seem simple. Matter falls in, never comes out. But Stephen Hawking uncovered a terrifying implication of this gluttony. Black holes might be erasing the universe's receipts, violating one of quantum physics' most sacred laws. This is the black hole information paradox, and it threatens to unravel our understanding of reality itself. Here's the problem. Quantum mechanics insists that information, the detailed properties of every particle that falls into a black hole, can never truly disappear. It might get scrambled beyond recognition, but in principle, it should always be recoverable. Think of it like burning a book. The pages turn to ash, but if you had perfect knowledge of every chemical reaction, you could theoretically reconstruct every word. But Hawking radiation, the slow trickle of particles black holes emit, appears to carry no such details. It's thermal noise, random static with no connection to what was swallowed. If that's true, the original information is truly lost, and quantum physics, the framework underlying everything from atoms to smartphones, is fundamentally wrong. The stakes couldn't be higher. If black holes really do destroy information, it implies our universe operates like a faulty hard drive, where data corruption isn't just possible but inevitable. Physicists have spent decades wrestling with this paradox, proposing everything from hidden alternate universes inside black holes to holographic projections where information is encoded on the event horizon like a cosmic QR code. But one of the most radical solutions emerged in 2012, the idea of firewalls. Imagine approaching a black hole's event horizon, expecting to cross it silently as Einstein predicted. Instead, you're vaporized by a searing wall of energy, a firewall generated by quantum effects tearing spacetime apart at the threshold. This violent solution preserves information by ensuring it never actually enters the black hole. Instead, it's incinerated and radiated back out as Hawking radiation, encoded in the ashes. The catch: firewalls defy general relativity's prediction that falling into a black hole should feel uneventful, at least until tidal forces shred you. The debate rages on. Some physicists argue firewalls are overkill, that subtle quantum entanglement can preserve information without apocalyptic physics. Others suggest the paradox reveals a deeper truth, that spacetime itself might be emergent, a sort of illusion woven from quantum bits. Every proposed solution feels like pulling a thread that could unravel the entire tapestry of physics. What makes this paradox so compelling isn't just the science, it's what it says about the limits of human knowledge. Black holes aren't just testing gravity or quantum theory. They're forcing us to ask whether the universe is inherently knowable. Every time we think we've solved the puzzle, the cosmos whispers back with a harder question. And somewhere in that tension between what we understand and what lurks beyond the event horizon lies the next great leap in our journey to decode reality. The moon's barren surface might seem like the last place you'd want to set up camp, but what if the safest real estate isn't on the ground but beneath it? Hidden under that dusty gray exterior lies a network of colossal underground tunnels, remnants of ancient volcanic fury that could become humanity's first off-world suburbs. These lunar lava tubes, some wider than city blocks and tall enough to swallow skyscrapers, formed billions of years ago when rivers of molten rock carved channels through the moon's crust, leaving behind hollow passageways as the lava drained away. What was once a geological afterthought is now the hottest prospect for future moon bases, and Japan's upcoming mission in 2025 could be the key to unlocking their potential. Picture these tubes as nature's perfect cosmic bunkers. Their rocky ceilings, up to 15 meters thick in some areas, offer near-perfect protection from solar radiation, micrometeorite storms, and temperature swings that can veer from 120 degrees Celsius at noon to -170 at night. That's like swapping a flimsy tent on an Antarctic glacier for a fortified castle. Early radar scans suggest some tubes stretch for hundreds of kilometers with stable environments that haven't changed in epochs. Scientists suspect these tunnels might even trap ice in their darkest recesses, providing not just shelter, but potential water reserves for thirsty astronauts. Japan's ambitious Selene 2 mission aims to map these subterranean labyrinths with unprecedented precision. Using ground-penetrating radar and gravity sensors, the orbiter will peer beneath the lunar surface like a cosmic X-ray machine, pinpointing tube locations, sizes, and structural integrity. The most promising candidate, the Marius Hills region, where NASA, a lunar reconnaissance orbiter, already spotted gaping skylights, collapsed sections of tube roof that act as natural stairways into the underworld. These openings could become the front doors of future lunar cities, with elevators lowering habitats and equipment into ready-made caverns below. But the real game changer isn't just avoiding surface hazards, it's how these tubes could revolutionize lunar construction. Instead of hauling bulky radiation shields from Earth or 3D printing fragile habitats from moon dust, we'd be retrofitting nature's pre-built architecture. Imagine inflatable habitats unfurling inside these giant tunnels, their walls reinforced by billion-year-old basalt. Solar panels could line the surface above, transmitting power through the rock, while vertical farms thrive in the constant, cozy temperatures below. Some engineers even speculate about sealing entire tubes to create pressurized cities, where you could stroll through underground parks without a spacesuit. The implications stretch far beyond shelter. These tunnels could be time capsules preserving the moon's volcanic history, their walls layered with clues about the solar system's violent youth. They might also harbor pockets of ancient ice or even microbial life that hitched rides on asteroids, making them scientific treasure troves. And for future Mars missions, perfecting tube living on the moon would provide the perfect dress rehearsal for inhabiting the even larger lava tubes discovered beneath the red planet's surface. What makes this more than sci-fi fantasy is how quickly the pieces are falling into place. Private companies like SpaceX are slashing launch costs, while advancements in robotics could send tunnel scouting rovers ahead of human crews. Japan's mission might soon give us the first detailed blueprints of our lunar basement, and if the maps look promising, those dark, silent tunnels could become the beating heart of humanity's first permanent outpost beyond Earth. The same volcanic fury that once shaped the moon's face may have unwittingly built our cosmic safe house, waiting empty all these eons for the flicker of human lights to bring it to life. The James Webb Space Telescope was supposed to confirm our cosmic origin story, but instead it's tearing pages out of the textbook. When astronomers pointed its infrared eyes at the earliest epochs of the universe, they expected to see infant galaxies, small and chaotic, just beginning to stitch themselves together from the primordial darkness. What they found instead were cosmic adults, massive, fully formed galaxies strutting across the stage when the universe was barely 2% of its current age. These galactic giants, some weighing as much as 100 billion suns, are the cosmic equivalent of finding a polished skyscraper in the middle of the Stone Age. Take Sears 93,316, for example. This galaxy was spotted as it appeared just 235 million years after the Big Bang, a blink in cosmic time. Yet its stellar population suggests it had already been forming stars for hundreds of millions of years. That's like discovering a 5-year-old child who's already graduated college. Even more baffling are galaxies like Glass Z13, whose disk structure is so orderly and mature that it defies everything we thought we knew about how quickly galaxies evolve. According to standard models, these behemoths shouldn't have had time to assemble. Dark matter halos the invisible scaffolding that helps galaxies form wouldn't have had enough time to gather sufficient gas. Yet there they are, gleaming in JWST deep field images, as if the universe hit fast forward. So what's really going on? One possibility is that our models of galaxy formation are missing something fundamental. Maybe dark matter clumped together faster than we thought, or early stars formed with freakish efficiency. Some theorists have even resurrected the idea of heavy dark matter, exotic particles that could have jump-started gravitational collapse earlier than standard models allow. Others propose that supermassive black holes lurking in these galaxies' cores might have acted as cosmic catalysts, accelerating star formation through violent feedback loops. But there's a more radical interpretation. What if the Big Bang wasn't the true beginning? Alternative theories like conformal cyclic cosmology suggest our universe might be one in a series, with remnants of a previous cycle seeding these impossible structures. It's a long shot, but the sheer existence of these galaxies forces us to reconsider even our most basic assumptions. The implications ripple far beyond astronomy. If galaxies could form this quickly, it reshapes our understanding of when and where life might have arisen in the universe. Imagine civilizations blooming in these ancient galaxies, billions of years before our solar system even existed. Or consider the fate of these cosmic titans. Did they burn out young, or do their descendants still shine somewhere in the modern cosmos? JWST discoveries are a humbling reminder that the universe loves to defy expectations. Just when we think we've pieced together the story, it tosses us a plot twist written in starlight. These impossible galaxies aren't just anomalies, they're cosmic breadcrumbs, leading us toward a deeper, stranger truth about how everything began. Every story has an ending, even the universe itself. As we peer into the far future, cosmologists paint three starkly different final chapters: the silent fade of heat death, the violent shredding of the Big Rip, or the cosmic encore of cyclic rebirth. Each scenario hinges on the universe's most mysterious player, dark energy, and whether its grip on spacetime will tighten, slacken, or reset entirely. Let's start with the most haunting possibility: heat death. Picture a universe where every star has burned out, every black hole evaporated, and every particle drifts so far apart that temperatures plummet near absolute zero. With no energy gradients left to power motion or thought, time itself becomes meaningless. This isn't a dramatic explosion or collapse, it's the universe exhaling its last breath into infinite stillness. The mathematics behind it is chillingly sound. Entropy, the measure of disorder, always increases. Given enough time, think 10 to the power of 100 years, even protons will decay, dismantling the last remnants of matter into a thin gruel of radiation. The cosmos becomes a graveyard where not even memory remains. But what if the end comes not with a whimper but a scream? Enter the Big Rip. If dark energy grows stronger over time, it could eventually overpower every force holding the universe together. First, galaxies would be torn from each other. Then, stars would unravel from their orbits. In the final moments, planets, atoms, even spacetime itself would be shredded apart. The trigger, a hypothetical form of dark energy called phantom energy, which escalates exponentially until the fabric of reality ruptures. Some models suggest this apocalypse could arrive in as little as 22 billion years, a blink compared to heat death's glacial timeline. The telltale clue: astronomers are already measuring whether galaxy clusters are flying apart faster than predicted, a potential early warning of dark energy's tightening grip. Then there's the most optimistic exit: cyclic rebirth. Imagine the universe as a phoenix where each death seeds the next incarnation. In this model, the current expansion eventually reverses, collapsing everything back into a singularity before rebounding in a new Big Bang. The evidence: mysterious patterns in the cosmic microwave background that some theorists argue are echoes of a previous universe. There's also the tantalizing possibility that dark energy could decay, flipping from a repulsive force to an attractive one. While current observations favor endless expansion, the cyclic model offers poetic symmetry, a universe without true endings, only transformations, the wild card in all this. We still don't know what dark energy is. Is it a constant force, as Einstein's cosmological constant suggests, or does it evolve, as theories like quintessence propose? Every measurement of distant supernova, every map of galaxy clustering brings us closer to an answer. Future telescopes like ESA's Euclid mission aim to track dark energy's influence with unprecedented precision, potentially ruling out one of these fates. What's truly humbling isn't just the scale of these scenarios, it's how they reframe our existence. Heat death renders all achievements temporary. The Big Rip makes them abruptly finite. Cyclic rebirth offers a strange kind of immortality. Yet in each case, the universe insists on a final lesson. Everything changes, even the rules themselves. Whether the cosmos ends in ice, fire, or renewal, one thing's certain: the story won't close on our terms. It's the ultimate reminder that we're temporary guests in a universe playing by its own clock. From invisible dark matter pulling the strings of galaxies to mysterious signals that might be alien hellos, our universe is stranger than fiction. We've explored worlds where diamonds rain from toxic skies, black holes that might erase the past, and galaxies so ancient they defy time itself. Every corner of the cosmos whispers secrets, whether it's the eerie silence of the Fermi paradox or the quantum threads instantly connecting particles across light years. These aren't just curiosities, they're clues in the greatest detective story ever told, one where each answer unravels two new questions. Think about that for a second. The same atoms forged in stellar furnaces now make up your hands, your eyes, even the thoughts racing through your mind. Carl Sagan said it best, "We are a way for the cosmos to know itself." And what better way to honor that than by looking up? The next time you step outside under a clear night sky, remember, you're standing on a speck of rock orbiting an ordinary star, surrounded by mysteries waiting to be solved. The universe isn't just out there, it's in you too. If these cosmic wonders left you hungry for more, hit that subscribe button. We've barely scratched the surface. The cosmos has endless surprises up its sleeve, and we're just getting started. Until next time, keep your eyes on the stars and your mind open to the impossible. After all, the universe never runs out of magic.